Okay, so yesterday I have introduced the multi-agent resource allocation problem and described different fairness and efficiency notions. And today I will turn to the algorithm point of view and describe various mechanisms for allocating goods among agents. And I hope I have some time to describe matching problems and the well-known Gale-Shapley algorithm for matching problems. So now we want to investigate how to allocate the resource among the agents. So we have seen that we can define the quality of an allocation from the efficiency point of view or from the fairness point of view. So the allocation mechanism will provide different guarantees regarding the efficiency or the fairness. To justify the relevance of the algorithm, we will also explore the axiomatic of mechanism. In fact, it consists in exploring whether the mechanism satisfies some desired axioms such as anonymity. So, in fact, you can see it as the outcome of the mechanism does not depend on the ID or the name of the agents. Neutrality is similar but applied to resources. So the outcome of the algorithm does not rely on the name or the ID of the resources. And we will also talk about strategy proofness. So an algorithm is said to be, or mechanism is said to be strategy proof if no agent has an incentive to misreport, to lie about his true preferences. So it does not have an incentive to try to manipulate the mechanism, the outcome of the mechanism. So we will see that the various mechanisms satisfies or do not satisfy some of these axioms. And we will also consider how the mechanisms can be applied. And we will see that many mechanisms are centralized, but we may want to use a distributed mechanism. So what are the cons and the pros of centralized mechanism and distributed mechanism? In fact, in a centralized mechanism, you have a central entity, which is called here a central coordinator, which is responsible for allocating the resource. So it means that all the agents have to communicate to the coordinator their preferences for the coordinator to be able to apply the mechanism. So, it needs to communicate the preferences. And so I say there is little communication because we assume that once the preferences are communicated, the coordinator won't have to communicate with the agent. He only has to execute the mechanism. So why we would like to use centralized mechanism? Because we have many results from economics. In fact, in economics, the most results consider the point of view of a central coordinator and do not consider a distributed allocation of resources. So we have many results from economics. And if you have a central coordinator, it is often easy to provide guarantees on the outcome of the algorithm and on the efficiency and the fairness of the allocation. So it's often easy to provide good results about the outcome. On the negative side, when you use centralized mechanisms, it means that the coordinator is the only one to be responsible for the allocation. So the agents, once they have communicated their preferences, they must completely have confidence in the coordinator, and they must be willing to communicate their preferences. In many real scenarios, in fact, if you consider that you have to allocate resources among companies, companies won't be willing to communicate all their preferences on the resources you may have to allocate to them. So, in fact, the agents may want to keep their preferences as private information, and they may not have full confidence in the coordinator. So, in this case, you have to you have to make the mechanism more distributed for the agents to be able to participate in the mechanism and to improve the implication of the agents in the mechanism. So in fully distributed mechanism, the agents, in fact, will negotiate over the resources and make locally agreements to exchange resources. So in distributed mechanism, we start from an initial allocation and we let the agents make deals among the resources, and we expect the system to converge to a stable outcome that could provide some guarantee of efficiency or fairness about the global allocation. So one of the positive, the advantage of such an approach is that the agents don't have to communicate their preferences. Preferences are kept private. It is more natural in many applications. So, for instance, if you think about bargaining in real societies, it's easier to implement this as a distributed mechanism. It is often easier to consider such mechanism when the agents have an initial allocation, and in fact, to reach another allocation, you need the agents to agree about the fact that they will exchange their current resource with another resource. And of course, it is more scalable as you don't have a central coordinator which have to compute a huge allocation with a large set of preferences. But the negative side of this approach, as you will see later, is that convergence is not always easy, and it is much more difficult to provide guarantees on the outcome because there is no central coordinator who controls the outcome of the process. So I will start with the well-known adjusted winner procedure. So it is a mechanism which can be used if you have only two agents. So it's a rule which is used in real life for divorce settlements, for instance, or to share international borders when you have conflicts between two countries on borders. So in this procedure, you can assume that agents have cardinal or additive preferences. And if we consider cardinal preferences, the agents are assumed to be weighted equally. That means that the sum of the utilities for an agent, the sum of the utilities for the resources is the sum of the utilities for the resources is the same for both agents. So if you sum all the utilities, you obtain the same numbers. You will see that it is important when we execute the procedure. So this procedure is nice because it is guaranteed that the outcome is envy-free, equitable, and Pareto optimal. So we have two notions of fairness that are satisfied, and we also have Pareto optimality. Sorry, Denis. But this fairness guarantees and Pareto optimality holds if all items can be split, and if your resources are indivisible, it may not be the case. By the way, the mechanism is also strategy proof. Is not strategy proof, but in fact, fairness and efficiency are only guaranteed when the agents report their true preferences. So that means if the agents lies about their preferences to manipulate the outcome, in fact, we will not have the guarantee of, we will lose the guarantee of fairness and efficiency. So how does it is executed? So as an input of the algorithm, each agent reveals her preferences for each item. Once we have the preferences of the agents, we will assign each item to the agent who values it the most. So if an item RK is preferred by agent I, we assign it to agent I, or otherwise we assign it to the other agent. Once we have done this, we don't have an equitable nor an envy-free solution. And if we don't have the weighted equally hypothesis, you can see that an agent will have to give a high score to each resource to obtain the resource. So this is why we try to avoid such case by restricting the possible utility. So once we have assigned each item to the agent who values the more, we will try to re-equilibrate the outcome. And in fact, we will transfer items from the richest agent to the poorest. And we will consider items in increasing order of the ratio between the utility of the richest agent and the utility of the poorest agents for this item. So I will show you this on an example. So we have two agents, we have 5 resources, and you can see that the sum of the utility for each agent should be the same. So 2 plus 10, 12, 14, 19, 20, and 10, 13, 18, 20. Okay. So in the first step, we assign the resources to the agent who values the more. So we obtain. Okay, so the example is not the same, but it will be okay. So we assign R1 to the second agent. The second resource is assigned to the first one, the third to the second agent, and the last 2 resources are assigned to the first agent. So we have an implicit tie-breaking rule where both agents give the same value to an object. We assign it to the first one. It don't have it makes no difference if we use this type of rule or we assign it to the second agent. So at the end, we can see that the first agent has a utility of 16 and the second agent has a utility of 11. So the first agent is the richest, and the second is the poorest. So we will transfer resources from the first agent to the second agent as we want to obtain an equitable and entry-free allocation. So to transfer these resources, we will compute the ratio of utility between the utility of the first agent and the utility of the second agent. And we will consider the ratio in decreasing order. So in this case, so okay, we have the ratio. So we first transfer the last resource. So we consider in increasing order the ratio. So we will first transfer the last resource. If you look at the ratio, we have 1. This is the minimum. So we transfer the last resource to the second agent. And we then obtained a utility of 14 for the first agent, and a utility of 13 for the second agent. So we have almost the same utility, but they are not equal. So we have to transfer one resource from the first agent to the second agent. The minimum ratio is for R4, but if we transfer R4, we will have only 10 for the first agent, and then R4 will belongs to the second agent, so we will have 17 for the second one. So we will have the inverse as we have here. So the second will be the richest, and the first will be the poorest. So we have to transfer a part of R4 to make both agents have the same utility, and to compute which part of R4 we have to transfer. So we want the utility of both agents to be equal. So here we have 14, and we will remove a part of R4, which is value to 4. So we will remove P of 4, and we will add this part to the utility of the second agent. So the utility of the second agent is 13, and if we give him a part of R4, as the value R4 to 3, the added value will be 3 by P. So we obtain, by solving this equality, we obtain P equal 1/7. So in this case, we will transfer the part P of R4 from the first agent to the second agent. But as you see, it means that we can split R4. If we can't split R4 is indivisible, we won't be able to obtain an entry-free and equitable allocation. And as at the beginning of the algorithm, we don't know which resources we will have to split to obtain an entry-free and equitable solution, we have to make the assumption that all resources can be split. So another mechanism, which is also well known in the literature, is the top trading cycle. So it is also a centralized procedure, but it can be used for any number of agents. but it is described. It can only be used in house allocation problem. So house allocation problems are multi-agent resource allocation problem where you give only one and exactly one resource per agent. In fact, it consists of problems where you have a set of agents, you have a set of houses, and you want to assign an house to each agent. Agent cannot share houses, and we want each agent to have an house. And we start with an initial endowment, so it means that each agent initially have a house, and they can exchange their houses. So as we will see later, in fact, house allocation problems with initial endowments correspond to house markets. So in the top trading cycle algorithm, we assume that the agents have ordinal preferences over the houses. And the advantage of TTC is that it returns a unique solution. So we will see that we can choose different cycle, but in fact, we always obtain the same solution. And this solution is Pareto efficient and belongs to what we call the core. And the core is the set of solution where no coalition of agents can make all its members better by exchanging the items they initially own in a different way. So no coalition would have an incentive to exchange the items in a different way to obtain better utility. So we have the guarantee to obtain a Pareto efficient solution, and it is also individually rational and strategy proof. So the agents don't have an incentive to manipulate, to misreport their preferences. And individually rational, you will see that when the agents move to another house, they always move rationally. So they always move to a better house, and they won't have to move to a worst house to then get a better house later. And it has been proved that in house market, in fact, TTC is the only mechanism presenting all these guarantees. So if you find another mechanism which has the same guarantees, in fact, it is equivalent to TTC. It is TTC. So how does it work? So in fact, we will build a bipartite graph where on one side we have the set of resources, of remaining resources in the market. So initially we have all the resources in the market. And on the other side of the bipartite graph, we have the set of agents in the market. And initially we have all the agents in the market. And we will make each agent in N points to a preferred resource in R. And we will make each resource in R points to its owner in N. And then we will look if we have cycle. And if we have cycle, we will implement this cycle and remove the agent which belongs to the cycle and the resource which belong to the cycle. We will remove them from N and R. So, an example. So here we have 5 agents and 5 resources as we are in a house market. So we start with the boxed allocation. So the first agent initially owns R5, the second one R1, and etc. And if we execute TTC, we will obtain the underlying allocation. So let's apply TTC. So we make each agent points to a preferred resource, which is in the market. So at the beginning, the first agent will point to R1. The second will point to R5, the third one to R1, the agent 4 to R3, and agent 5 to R4. So this is this, this, and so on. And we make each resource point to its owner. And then we try to find a cycle. So we have the guarantee that there exists a cycle. And in this case, we can see that we have a cycle here between R1, A2, and R5. So we will implement this cycle. So we will give resource R5 to A1 and resource R1 to A2. And you see, we obtain the underlying allocation for the agent 1 and the agent 2. We remove agent 1 and agent 2 and their resources from the graph, and we update the graph with the remaining resources. So now we have a new cycle, which is in fact a cycle between agent 3 and a resource. That means that we will assign R3 to A3, and we remove the agent and her resource from the graph. So in fact, the agent keeps his resource and is removed. We update the graph, and we obtain a final cycle between A4, A5, so we give R2 to A4 and R4 to A5. And we remove both agents and both resources. And we obtain an empty graph, and we have finished. So you can see that the outcome solution is Pareto optimal. And you can check that it is in the course. So no coalition of agents could obtain better resources by exchanging their resource in another way. Yes?
If you have indifferences, do you have some problems, or?
There is no indifferences. Yes. You assume that you have strict preferences. Yes. Okay. Okay. So the top trading cycle and the adjusted winner are a centralized procedure. Now we will see a procedure that it is between centralized and decentralized. It is quite difficult to classify it because the first part of the procedure is centralized, but the second part can be executed in a decentralized way. So this is picking sequences. And in picking sequences, you start from a predefined sequence of agents, which is computed in a centralized way. So you have a sequence of agents. And then the agents will pick a resource at their turn. So you give an ordering of a sequence of agents, and each agent pick a resource among the remaining resources. It's like what you do when you make teams at sports in college or lycée. So you have two persons, and at her turn, the person choose one of the member of a team. So when the agents choose their preferred resources, the agents are said to be sincere. So in this case, we have sincere picking sequences. And there are different types of sequences. You can imagine if you have 2 agents and 6 resources. So you can say that the agents, the first agent pick 3 times, and then the second agent pick 3 times. But you will see that this should not be fair for the second agent. So you can imagine alternating sequence. So where you have 1, then 2, agent 1, then agent 2, and so on. And you can also imagine agent 1, agent 2, then 2, 1, and then you have to decide for the last turn which agent will start. So alternating sequences are sequences where the agent is restricted to a balanced sequence. So in fact, you have A1, for instance, A2, A2, A1. In round-robin picking sequences, you can divide the sequence as different rounds, and in each round, all the agents pick exactly once. So and all rounds are identical. So in this case, you have 1, 2, 1, 3, 2, 1, 3, 2, 1, 3, 2. So at each round, you have 1, 3, 2, and you repeat the rounds. And when you have the same number of items and the same number of agents, and each agent appear exactly once in the sequence, so all the agents will appear in the sequence, you have a mechanism which is called serial dictatorship with interesting guarantee. So we will give an example. So in this case, we have an alternating sequence with agent 1, 2, agent 2, agent 1, agent 1, agent 2. So here we have the preferences of the agents, and here we have the allocations. At the beginning, the allocation is empty for both agents. So the first agent will will make a we assume the agents made sincere choice, so he will take the best resource among the remaining resources. So here you have all the remaining resources. So it takes R1. Then agent 2 takes R4. Then it is again the turn of agent 2. So agent 2 has already taken R5. R1 is already taken by the first agent, so she will take the resource R2. And so on. So next it is the first agent. The first agent takes R4. Then again, agent 1. So agent 1 takes R6. And then the last agent takes the last remaining resource R3. Okay. So we have interesting guarantees about the picking sequences. So in the case of the serial dictatorship, we can guarantee Pareto optimality and strategy proofness. And so serial dictatorship, if we come back to the definition, it is when we have the same number of agents as the number of items. So in this case, it is Pareto optimal and strategy proof. In fact, if each agent has only one pick only once, it has no incentive to take another resource than the resource he prefers, because he's the only one he will obtain. And under additive preferences, in round-robin picking sequences, we can show that the return allocation is envy-free up to 1 good, but it is not guaranteed that it is Pareto optimal. So why it is envy-free up to 1 good? So if we return to the definition, so in round-robin picking sequences, we have a set of rounds, and in each round we pick in the same order. So if we look at the agent 3, So agent 3 can envy the resource picked by the first agent, because the first agent has picked before her, but agent 3 won't envy the resource of agent 2 and the second resource taken by agent 1. The next round, agent 3 doesn't envy the resource picked by agent 2 and agent 1. And at the last round, it won't envy the resources picked by agent 2. So the only, as utilities are assumed to be additive, in fact, the envy of agent 3 can be eliminated by removing from agent 1 the resource picked before her first pick. So we have envy free up to 1 good as defined yesterday. Okay, and so we have seen that in round-robin picking sequences, we don't have the guarantee of Pareto optimality, but it has been proved that if the allocation is in fact, we can define a type of allocation which are said to be sequenceable. So an allocation is said to be sequenceable if it can be obtained by a picking sequence. And it has been proved that every Pareto optimal allocation is sequenceable. So in fact, what does it mean? It means that every Pareto optimal allocation can be obtained by a picking sequence. So some picking sequence do not lead to a Pareto optimal allocation, but all Pareto optimal allocation can be obtained by a picking sequence. Okay. So I will finish with allocation mechanism by describing a fully decentralized mechanism. So in the decentralized mechanism, as I said before, we start from an initial endowment and we let the agent make deals of exchange of resources. So we assume that they make rational deals, so improving deals for both agents. We let the agent exchange resource, and we hope that the system will converge to a stable allocation, and we study the guarantee, the properties of the outcome. So in this case, we have 4 agents with 4 resources. Initially, the agent has their worst resource, and we let the agent exchange resource. So in this case, I assume that first agent 1 exchange with agent 2, so they both improve their allocation. Then agent 2 exchanges with agent 4. They both make a rational deal. Then agent 2 exchange with agent 3. And that's all. At the end, we are happy since all the agents have their best resource. And we have converged to a stable allocation. The agent won't try to exchange anymore. So the first good point is that we can show that we will always converge a stable allocation in the additive case, as each exchange is rational and the utility is upper bounded for all the agents. But in fact, we have seen one sequence of exchange, but the agent could have exchanged in a different way. So if we restart from the initial allocation and we consider another sequence of exchange, in this case, agent 1 exchanges with 3 and 2 with 4. And then, and that's all, I think. Yes. And from this allocation, we don't have any more possible deals involving rational deals involving two agents. And in fact, we prove that if we have okay, so we prove that if we have n agents in some situation to reach Pareto optimal allocation, we may need to make a deal involving n agents, involving all the agents. So if we restrict the exchange to a bilateral exchange involving only two agents, we may reach an allocation that is not Pareto optimal. In this case, the allocation is not Pareto optimal, and the Pareto optimal allocation can only be obtained by an exchange involving all the agents, so the four agents. So with bilateral deals, convergence is guaranteed, but Pareto optimality is not guaranteed unless we allow for a exchange involving all the agents. But there is a specific case where we can guarantee Pareto optimal allocation. It is in the case of single-peaked preferences. So single-peak preferences is what we call a domain restriction. We have assumption on the preference structures of the agents, which allows us to consider only a subset of preference structure. So in fact, in single peak preferences, the items are organized on an axis, and you have a peak on this axis, which is the most preferred preference. And when you rank the resources, you can only go from to the left or to the right. So in this case, you consider a size of t-shirts. The preferred size, so you have an axis with the size of the t-shirt, so S, M, L, XL, and etc. You have a peak. Here my peak is M. And if my most preferred size is M, then the size preferred just after M can only be S or L. It cannot be XL or XXL. So in my case, it is S. So the next size preferred after S can be XS if it exists, but in this case, it doesn't exist, so it will be L. And then it can only be XL and XXL. So these preferences are single-peaked, but in this case, the preferences are not single-peaked. As you can see, my peak is M. So after I prefer S, so it's okay. But I prefer XL to L. And you see that when I go from the peak to the right side or to the left side, it is not only decreasing. So the preferences are not single-peaked. So it is quite natural in many settings. For instance, in political preferences among parties, it is quite a natural assumption. So it is often considered in economics. And if we return to our problem of the size of the exchange in distributed setting to guarantee Pareto optimality, we can demonstrate that in under single peak preferences, bilateral exchange guarantee Pareto optimal allocation. So if we return here, we don't have single peak preferences, and we don't have the guarantee of Pareto optimality, but we can have the guarantee of Pareto optimality if the preferences among the resources are single peaked. And we have a proof of maximality of the domain restriction. Okay. 30 minutes? Okay. So I will have some times to to introduce matching problems. So in fact, matching problems are problems where you have the same, the size of the set of items and the size of the set of resources are the same. So it is what we call house markets, or I have used the term house allocation problem. The difference is that in house allocation problem, you don't have an initial endowment, and in house markets, each agent initially holds a resource. So when I introduced TTC, I say that it can be applied in a house allocation problem with an initial endowment. So in fact, in house markets. So TTC can solve problem in house markets. Most of the time in this type of problem, preferences are ordinal. And if our objective is to find a Pareto optimal matching and a matching which is in the core, we can use TTC as explained before. Just a note side, in fact, in house market problem, the fairness notion of entry-freeness has little interest, because an agent who don't obtain a first resource will be envious, as each agent obtains only one resource. If this resource is not your top resource, and your top resource is assigned to another agent, you will be envious of this other agent. So it is very restrictive to find an envy-free allocation in house market problems, because an envy-free allocation means that all the agents obtain their top resources. So it means that all the agents have different top resources, and you can easily check that an envy-free allocation exists or not. So we will consider other fairness criteria that envy-freeness. So in fact, in house market, we will consider Pareto optimality, and we will consider the rank of the resource we obtain. So if we have house market, as I said before, we can use the top trading cycle. If we have an house allocation problem, most of the time we can use the serial dictatorship algorithm. So it is a picking sequence where the number of items equals the number of agents. And it has been proved that in this setting, all Pareto optimal allocation can be obtained by the serial dictatorship. And when you use, so we have to give an order sequence of agents. So to compute this sequence, we can use a uniform lottery. So we can generate randomly the sequence with equal probability over the sequence. And in this case, the mechanism is called random serial dictatorship. So that's for house markets, but so yes. So in house market, we may want to give a stronger guarantee than Pareto optimality on the outcome of the solution. And one notion is popular matching. So popular matching, a matching is quite related to voting theory. In fact, in a popular matching, we will make, in popular matching theory, we will make the agent vote about their matching. So a matching is said to, given two matching M and M prime, each agent will vote for M or M prime. So they vote for M if the resource they obtain in M is preferred to the resource they obtain in M prime. Otherwise, they vote for M prime. So if the situation is the same in both matching, if they obtain the same solution, they abstain. And then we count the number of votes for M, we count the number of votes for M prime. So in fact, we count the number of agents who prefer M to M prime, and we count the number of agents who prefer M prime to M. And we say that matching M is at least as popular than N prime if it obtains at least as votes than M prime. So we count the number of votes for M. If it is at least as large as the number of votes for M prime, M is said as at least popular as M prime. And a matching is said popular if it is at least as popular as any other matching. So it means that it will be preferred by the largest set of agents. And when we have no indifferences, so no agents who abstain, we can say that a matching M is popular if it is preferred by a majority of agents over a matching M prime. So it is a stronger than Pareto optimality. It is more demanding than Pareto optimality, but it is quite natural notion to make the agent agree on the relevance of a matching, because you can explain to the agent that we choose this matching because it is preferred by the majority of the agents in the system. Nonetheless, the existence of a popular matching is not guaranteed. As you can see, in this case, there exists a popular matching. In fact, the boxed matching is a popular matching because it is preferred by a majority of agents. It is quite easy to see because the first two agents obtain their top resource, so they will prefer this matching to any other matching where they won't obtain their top resource. So this is a popular matching, but if you have all the agents have the same preferences, there is no popular matching because you have to give the first resource to one agent, which will agree on this matching. The second one will prefer matching where he obtains his top resources, and the third one will obtain his third resource and will prefer all other matchings because we can obtain R2 or R1. So in this case, you don't have there does not exist a popular matching. And it has been shown by Abraham that there exists a polynomial time algorithm to decide whether a popular matching exists or not, and to compute popular matching when it exists, because the algorithm is constructive. And in fact, the algorithm relies on a characterization of popular matching given also by Abraham. And Abraham says, so he demonstrates that matching M is popular if and only if every first item, so a first item is a resource that is ranking as first by at least one agent. So in this case, R1, R5, R3, and R4. So every first item is matched in M. Is M to a first agent. It's more than to a first agent, and every agent obtains a first item or a second item. So there is something that we must be very careful in this case, that because a second item is not necessarily an item that is ranking second in the ranking of the agents. In fact, a second item is the item an agent ranks the higher, which is not a first item. So in this case, for agent 1, so our first item is R1, and our second item cannot be R4 as it is ranking first by the agent 5. It cannot be R3 as it is ranked first by agent 4. So it is R2. So the second item is R1. The first item is R1 and the second is R2. And Abrams demonstrates that in a popular matching, every first item is matched to a first agent, and every agent obtains a first or a second item. So if we return to this matching, so every first item R2 and R1 are matched to a first agent, to an agent who ranked it first, and the third agent obtained a second resource, which is R3. So this is we can show that this is a popular matching. In the case here, you can see that this matching is not popular because agent 4, the second house of agent 4 is R5, and the agent obtained R2. So this matching is Pareto optimal, but it is not popular. So you can see that popularity is more demanding than Pareto optimality. And in this case, so here you have to remove so here A3 obtains R2, not R3. And the third agent obtained last ranking resource, but this resource is a second resource, as all other resources are ranking first by the other agents. So in the case where A3 obtains R2, so not R3, the matching is popular, even if one of the agents obtained a last resource. Okay. So I will not describe the algorithm to compute a popular matching, and I will go to the last part of yes.
One popular matching exists. Is it a unique one? No.
No, you can have a different popular matching with a different worst case rank. So if you can then try to maximize the worst rank of the agents. And when you don't have a popular matching, you can try to find the most popular one, which is the matching which is popular among the largest set of agents. And you also have different most popular matching. Okay, so I will like to finish with what we call two-sided markets. So in fact, in all what I said, I consider that I have agents who have preferences over resources, and we have resources. But in some resource allocation problem, in fact, we have agents which have resources over items, and items have which have preferences over items, and these items are not objects, and they have preferences over the agents. For instance, if you want to assign student to university, like in Parcoursup, Students have preferences over universities, but also universities have preferences over students. And in this case, you have what we call two-sided markets, as the preferences are in both ways. So we say in this case, we have two sets of agents, A and B, and agents in A have preferences over the agents in B, and agents in B have preferences over the agents in A. So it is what it is called in the literature marriage problem, and I will talk about hospital resident problem, I prefer, because if you talk about marriage problem, you have to rank partners. So I will avoid to rank men and women, and I prefer to rank hospital and residents. So this is a very current problem. So it is the problem of Parcoursup when you want to assign students to universities. But you may also want to assign students to courses, and courses, in fact, teachers in the course may have preferences over the students, depending of their marks or of the courses they have already attended to. You may also have preferences, two-sided preferences in student to project when you have a professor submitting project to students. The professor may have preferences over the students because of the knowledge they have already get in courses. And it is also a problem in kidney allocation problem. So in kidney allocation problem, you have kidneys and you have patients, and you have to assign kidneys to patients. So in fact, you have two-sided preferences because of the compatibility of the kidneys to the patient. And you also have preferences in kidney allocation. Some patients come with a member of their family which can give that kidney, but the kidney won't go to the patient who comes with the member of the family, but it may go to another patient with another donor which will give you a kidney. So you have cycle of exchange in kidney exchange which can be represented with a two-sided market. So we will talk about the hospital resident problem to formalize it. So we have a first set of agents, which are the hospitals. We have a set of residents, which are the second set of agents. So you can see that the size of the sets may be different. In the hospital resident problem, we assume that each hospital has a capacity, which is the maximum number of residents it can get. And each hospital has preferences over the residents. Here we will suppose that the preferences are strict, and each resident has preferences over the hospital, and this is also strict preferences. And we want to assign, to make an assignment. In fact, more than that, we want to make a matching, because an assignment is in fact a set of couples where we match one resident with one hospital. And in a matching, we have more than that, we have constraints. In a matching, we have a matching is in fact an assignment, so a set of couples such that each resident is only one match once in the matching, so it appears only once in the set of couples, and every hospital do not exceed her capacity. So we don't have more residents assigned to an hospital than its capacity. It can be lower than, yes. Yes. But if we have much more residents than the sum of the capacities, we want each hospital to be to fulfill its capacity, in fact. So yes, here we suppose that the number of residents is equal to the sum of the capacities. So here we have an example. So we have the resident preferences. So here I have 3 residents, and I assume that I have 3 hospitals with the capacity of 1 for each hospital. So resident has preferences, strict preferences over the hospital, and hospital have strict preferences over the resident. And the matching is the boxed allocation. So in fact, if you have the allocation for the resident side, you can deduce the allocation for the hospital. It's just to be easy to read. I have mentioned the allocation on both sides. So in my matching, I have 3 couple, R1, H1, R2, hospital 2, R3, hospital 3. So this is the reverse. And in such a problem, we want the first requirement about the solution is that the solution is stable. In fact, the solution is stable if there is no pair of agents who prefers to be together than being with their current assignment. If you make the comparison with men or women, couples are stable if no woman or no man prefer another man or woman than the one she is married with or he is married with. So we want the solution to be stable, and in my case, you can see that the couple R3H2 is not stable. So no, it's not stable because R3 prefer to be with H2 than with H3, and H2 prefer to be with R3 than R2. So in this case, my matching is not stable. There is an unstable pair. So R3 and H2 will want to quit their hospital and resident to be together. So the desired properties of matching mechanism are often neutrality and anonymity. So in neutrality, no resident should be favored, and in anonymity, no hospital should be favored. Stability, as I mentioned, matching M is stable if there is no unstable pair in the matching. So there is no pair of resident hospital such that the resident and the hospital of the pair would prefer to be together. And we also want strategy proofness of the algorithm. So we don't want the resident or the hospital to have an incentive to give another ranking than her true ranking to try to have a better hospital or a better resident than the one they obtain when they give their true preferences. And to solve this problem, most of the time, we use the Gale-Shapley algorithm. So here I apply it for residents, so resident-oriented Gale-Shapley. And in fact, Gale-Shapley shows that every instance of resident hospital problem admits a stable matching. And the resident or the algorithm of Gale-Shapley allows for computing a stable matching. So how does it run? So in fact, we have several iterations, and at each iteration, a resident will apply in an hospital. So she will apply to a favorite hospital, and the hospital can say, okay, you can come in my hospital, or it can refuse the proposal of the resident. In fact, the hospital will refuse if it is already matched to a resident that he prefers to the resident who make the proposal. If the hospital is not matched to a resident, or he still have he did not achieve its capacity, so it still can take residents. So if the hospital can still take residents, or it accepts the proposal, or if it is matched to a resident that is less preferred than the resident who makes the proposal, he will quit his current resident, and he will accept the proposal of the new the resident. So residents make proposal. The hospital who receives the proposal can accept or refuse. He refuses if it is already matched to a resident that he preferred to the one who makes the proposal. Otherwise, it accepts the proposal. If it is not matched, already matched, it's okay. The resident come. If it is already matched to a resident, he will quit the resident, which is less preferred. So why Gale-Shapley is a powerful algorithm for solving matching problem? First, it is a linear time algorithm for computing a stable matching, and you can efficiently solve the problem. Second, it has been proved that when you apply it, when residents apply to hospital, it is what we say resident optimal. That means that each resident will be assigned to the best hospital that she could be achieved in any stable matching, so that there is no other stable matching where the resident will obtain a better hospital. The algorithm is also truthful, so it means the agents don't have an incentive to misreport their preferences. It is also neutral and anonymous for residents. So anonymous for residents, it means that whatever the sequence of residents you take as input, it will lead to the same stable matching. So you don't care about the sequence of residents who makes the proposals. I will come back later to the counterpart of the algorithm. So I will show you an example of the execution. So in this case, I have the resident preferences and the hospital, and the resident will propose to the hospital. So we assume that we take the sequence R1, R2, R3, R4, R5 as the sequence of residents. So we start with R1. So R1 will make a proposal to a first hospital, so H1. H1 is not matched to any resident. So H1 will accept the proposal, and we will match R1 and H1. Then R2 will propose. R2 will propose to H1. H1 is already matched to R1. So H1 will refuse the proposal because he received a proposal from R2 but it is already matched to R1, which is his preferred residence. So he refused the proposal of R2. So R2 will then make a proposal to H2, her second hospital, and H2 is not matched to any residence, so it will accept the proposal. So at the second iteration, we have R2 with H1 and R1 with H1 and R2 with H2. Then R3 will make a proposal to a favorite hospital, H2. H2 is already matched with R2, and he prefers R3. So there is a yes. H2, so H2 will accept the proposal of R3 and will quit R2, which was previously matched with her. So R2 accepts the proposed to H2, who accepts, and R2 is no more match. So we return to R2. R2 has already proposed to H1 and H2, so he will then propose to H5. H5 is not matched, so H5 will accept, and we obtain the matching R1 with H1, R3 with H2, and R2 with H5. We then make R4 then make proposals. R4 will propose to H3. H3 is not matched in the matching, so H3 will accept the proposal. And then we turn to R5. We propose to H2. H2 is matched with R3. So he prefers R3 to R5, so he refused. R5 then proposed to H3. H3 is matched with R4, which is preferred to R5, so H3 refused. R5 then proposed to H1, H1 refused, and R5 proposed to H4, which is not matched, and H4 accepts. So at the end, we have the final matching, which is in yellow on the slide. And you can check that the matching is stable, so you can't find a pair of agents who prefer to be together than with the one in the matching. Okay, but we have applied the algorithm with the resident making proposal. We could try to apply on the other side, and you can do the same on the other side. And in this case, the algorithm will be optimal, but optimal for the hospital. In fact, if you apply it from the resident side, it is optimal for the resident, but it is not optimal for the hospital. So that was my remark on this side. On this slide, so the counterpart of the Gale-Shapley algorithm is it is optimal, but for the side who proposed. So if the resident proposed, it is resident optimal. If the hospital proposed, it is hospital optimal, but it is not optimal for the other side. So great. So Gale-Shapley is the algorithm which is used in Parcoursup. So it is why in Parcoursup you have to rank your choice to have a strict ranking. And guess on which side it is applied? university. In Gale-Shapley algorithm, in Parcoursup, it is applied from the university side, so it is university optimal, but not student optimal. Yes.
Just a question. Well, supposing there are a lot of people, a lot of hospitals.
Yes.
Is the hospital optimal solution very different from the resident optimal solution, or they can be very different?
Yes, they can be very different. In extreme, you have example where you have a very different solution. Yes. Okay, and if we talk about the interpretability of the procedure in Parcoursup, in fact, you see, to understand the outcomes of a procedure, you can easily, even as a computer scientist, you can easily understand the procedure. You have guarantee on the procedure, so you can see that it is not strategy proof. Students and the university don't have incentive to misreport their preferences. The solution is stable, and so on. But to really understand the outcome of the algorithm, you need to have all the preferences of all the students and to check the correct execution of Gale-Shapley. And of course, it is unrealistic to have all these preferences. Okay, so I mean, 2, 1, 2. So to conclude, I have presented a Gale-Shapley algorithm for two-sided markets. You can explore other kind of fairness criterion, such as Pareto optimality, maximizing the sum of the utilities, as I presented in one-sided market. You may also want to maximize the rank of the worst of agents or maximize the product of the utility as the Nash product. So there are a literature on computing such allocation. And there are also works on popular matching in two-sided markets. One good point in two-sided markets is that the existence of a popular matching is guaranteed in two-sided markets, whereas it was not guaranteed in the one-sided market. And in this case, you can have popular matching of different size. And the question is to find a maximum size popular matching. So a popular matching that is popular among the largest set of agents. And one other good point about popular matching in two-sided market is that any stable matching is a popular matching. And as Gale-Shapley algorithm always find a stable matching, you can use Gale-Shapley algorithm to find a popular matching. So the matching returned by Gale-Shapley is stable, but it is also a minimum size popular matching. If you want to compute a maximum size popular matching in the two-sided setting, you can apply an algorithm described by Garden-Forth, which is in fact a two-stage Gale-Shapley. So it applies Gale-Shapley from one side, and then, if I remember well, it applies Gale-Shapley on the other side, and it obtains a maximum size popular matching at the end. So popular matching are quite interesting in two-sided markets. Okay, I had related topics, but I don't have time, so I will end the presentation.